Hi guys, welcome back. This is the last example that we have for mechanical translation systems. Okay, and the significance of this example is we have a spring and a damper in series. Okay, and we want to see how we can actually handle this. And also, I'm gonna correct myself on the number of ODEs that from the beginning of of this chapter, we mentioned that the number of ODEs is in fact equal to the number of inertia elements. We want to see if that's accurate or no, and we want to basically correct ourselves. So let's get into it. Whenever you have a spring and damper in series, what we can do is we can throw a massless node between them. So I'm going to call this one as M1 equal to 0, okay, or M2 equal to 0. And I'm going to treat this massless node as a mass, okay. I'm going to basically draw a free body diagram for it. I'm going to put the equations of motions for it, okay. But when I do the equations of motion at the very end, what I would do is I would basically substitute the value for mass m1 as 0. Okay, so the four-step approach would be exactly the same. The only thing that's going to change is at the end, when you write down the equation of motion, instead of m1, you just substitute as 0. Okay, so let me just start the four-step approach, and it's going to become a little bit more clear when we do the solution. Okay, so let's go ahead and first write down the elements in the system. Okay, so you would see that I would have inertia, I would have stiffness, and friction. I need to comment on the number of ODEs and also sources. I forgot to put the sources first. Okay, so sources and the ODEs. Okay, so if you look at the system, I have only one inertia element, M, but I added a massless node, which is M1 equal to 0. Yes, this is my massless node. I'm going to treat it as an inertia element. The next one is a stiffness. I have a spring here. And the friction, I would assume that there is a viscous friction model here. The sources, the only source that I have for this system is the external force, so Fa, as a function of time. And for the number of ODs, if I would like to, if I wanted to go with the same direction that I had before, okay, and I would say that, okay, I only have one mass element in this system, or mass in the system, I would end up with only one ODE. I'm going to correct myself a little bit, okay? So I would say that with the number of independent motions in the system, I'm going to end up with ODEs. So I have two independent motion, which is motion Z1 and Z2, the motion of mass M and the massless node. So because of that, those two independent motions, I'm going to end up with two equations. Good? Okay. So step one, let's go and select our coordinate system. Okay. For the coordinate system, I would need two independent coordinate systems, Z1 and Z2. Okay. And I'm going to just work with the coordinate systems that are already given to me as Z1 and Z2, both of them pointing to the right. Okay. So Z1 and Z2 are the ones that we are working. Step two is basically isolating my inertia elements. So look, I have one mass, which is M, and I have a massless node, and I'm going to treat this massless node as a mass. Okay. So this is going to be Z1 and this is going to be Z2. Okay, great. Now I'm going to go to step 3, which is the free body diagram. The most important step, yes? So this is going to be few CSR. Okay. Friction. Look at the system. My damper is here. Yeah. So let me just change the color. My damper is here. And if you look at this damper, you see that only one side of this damper is moving. The other side is clamped to the wall. The side that's moving is actually moving with the massless node, M1, which is the velocity b z dot 2. The only thing that you need to take care of it is basically the direction of this motion. And you guys know that the friction force is always opposing the direction of motion. If you assume that the box is going to the right, this is going to go to the left. Good? Okay. So friction is gone. Next one is the external. This one is easy. If you look at the setup, you see that you have only one external force, okay, Fa, and the direction and magnitude of that guy is given to you as well. The next one is the weight. I do not have any motion on the vertical direction, so I would neglect the weight. The contact's the same. I have normal reaction force from the surface here, which I'm going to neglect because I do not have any motion on the vertical direction. The next one is the spring. Note that I have a spring here. Yes? So for the spring, you notice that both ends of that spring are moving. Yeah? So you need a clear assumption. So let me cross out these guys. You need a clear assumption between Z1 and Z2. Okay. So between Z1 and Z2, which one do you think moves more than the other one? Well, again, just like the previous examples, I would look at the direction of power flow. Since power actually flows into the system from the side of M and Z1, and then it's going to be transferred to M1 and Z2, I think it's reasonable to assume that Z1 is greater than Z2. Okay. Now, with this assumption, I would come here and I would make inside the parentheses positive. Yeah. Now figure out the direction. Okay. Assume you are the spring. Okay. And you also assume that Z1 is greater than Z2. So what we are going to do is, again, we are going to grab the pin and the hammer and pin the one that moves less to the wall. Between these two guys, you notice that M1 moves less. I'm going to pin this one to the wall and move M in the positive Z1 direction, which is moving it to the right. Yeah. If I move M in the positive Z1 direction, do you think that the person here is going to be stretched or it's going to be squeezed? Well, it's going to be stretched, yes? Okay. When the person is stretched, it's going to push back. Good. And that's your spring force. The next one is rope. I do not have any rope in this problem. I'm done. Yeah. So I can easily navigate to step 4, which is the equations of motion. Okay. In the step 4, I would write down the equation of motion. Summation of forces along Z1 equals to M Z1 double dot, and summation of forces along Z2 equals to M1, which is my massless node, Z2 double dot. This is 0 because it's massless. Okay, so the second equation is equal to 0. Okay. Let's look at M and Z1. See that I have one force here and one force here. FA is in positive Z1 direction, whereas the force of the spring is in negative Z1 direction. Okay, so this is going to be FA minus, or FA of T, minus K Z1 minus Z2 equals to M Z1 double dot. Similarly, if you look at M1 and the forces, I would have one force here, which is the force of the spring. It's on the positive Z2 direction, and one force here, which is the force of the damper, and it's in the negative Z2 direction. Yes, so this is going to be K Z1 minus Z2, yes, minus the force of the damper, which is B Z dot 2 equals to 0. Okay, so looking at these two equations, let's bring all the dynamic terms on one side and keep everything on the other side. I would have FA of T equals to M Z1 double dot plus K Z1 minus Z2. Yeah, and also the second equation is already actually sorted out. Yes, so it's going to be 0 equals to K Z1 minus Z2, okay, minus B Z dot 2. You guys note that this is a linear equation, yes? Okay, so since it's linear, let's check for the signs and the family members. In the first equation, I have two families, yes? Family of Z1 and family of Z2. For the family of Z1, I have two members, Z1 and Z1 dot dot, both of them positive. For family of Z2, only one member. So no sign mismatches within the families in equation 1. Also, in the equation 2, I have two families, Z1 and Z2. For Z1, I have only one member. For Z2, I have two members, Z2 and Z2 dot. Yes? And you see that both of them are negative, so there are no sign mismatches within the members of each family. You can safely box this equation. Okay. Once again, guys, what was the significance of this problem? The inclusion of massless node and correcting ourselves with the number of ODEs. We mentioned that when you have a spring and a damper in series, you can always throw a massless node in between them, okay, and follow your four-step approach. Also, the number of ODEs is in fact mandated by the number of independent motion in the system. Okay. If you found this video helpful, please subscribe to the channel and follow the full list of videos that we are building our way towards intelligent control and autonomous robotics. Thank you.